Okay, good afternoon, everyone. It's my first experience of outputting in this kind of strange new world. So you can see what I'm about to talk about from the title, but what I'd like to tell you is how I got there as a problem, and that is the connection with category theory. There's no applications of category theory here, I'm afraid, so you can stop me now if that's a necessary condition. Anyhow, so I went to a very nice meeting in Calgary pretty well a year ago, and a lot of the talk was about categories with differential structure. And I got interested particularly in Cartesian differential categories. And this is a quote from the paper there. It says, "The goal of the present paper is to develop an axiomatization which directly characterizes the smooth maps." And then it goes on to negate the first part of the sentence. In other words, to characterize the co-Kleisli structure of differential categories. The paper was written after a paper in differential categories. So what they do in that paper, Luke, Cockett, and Seeley, is they justify their axioms of Cartesian differential categories by reference to other categorical structures. So everything fits together nicely, so that's fine. But there's still a question as to whether or not it actually directly characterizes the smooth maps. And that's really a natural question for a logician. So I got interested in it then, and maybe I'll say a little bit more about it. And that led, so I'm actually not attacking that question, but a related question. And I think the techniques in attacking the related questions should help with this question. So let me just say briefly what Cartesian differential categories are. A minute. So they're based on categories with commutative monoid structure in every form set, but they're not enriched in it, they're only left additive. So the model you could take, say, is vector spaces and all functions as opposed to linear functions. And since you add up functions pointwise, it'll be left additive. But you see a morphism is additive if the right composition is additive. And then there's some natural compatibility conditions that the projections are additive and tupling preserves additivity. You don't need to say that the terminal object is additive, because you get that anyway from the enrichment. So the standard example that we want to think of is finite powers of R and smooth maps. And that's, I'm basically assuming everyone knows what I'm talking about, but anyhow, just very briefly, the gradient is defined as this vector of partial derivatives. Gradient of V is the derivative of V at x1 at V and so forth. And you can scale that up to differential if the output of F is a tuple, an M tuple, by regarding F as a tuple of unary functions, taking all the gradients and using them to define the differential. So differential of F at V is the linear function, which when you apply it to V, gives you this tuple of dot products with the various gradients. And anyway, everyone uses those ideas. What are the axioms of Cartesian differential categories? So here they are. And they're actually all pretty natural, even though when you write it in categorical terminology, it's hard to read, I think. They just say obvious things like differentiation is additive, the corresponding thing for zero I've missed out. And when you make a derivative, so d of f is from x squared to y, but derivative is going to be linear in the second argument, as we just saw, because it's just a product of the Jacobian matrix with something with the second argument. So you get the second additivity in the second argument, a bunch of things you would expect for a tupling, then the chain rule, which writes like that in categorically. And then this interesting thing that the second argument is not only additive, it's also linear. And what we mean by something.
Gordon, sorry to interrupt you, but your voice is
fine before we put on the headphones.
No, your voice is stuttery, and some people are suggesting turning off your video to reduce.
I can take the headphones off if that. Oh yeah, sure. Let's try that.
Try different things.
I'll try.
Yeah, some people are saying that maybe a headphone thing.
Is my voice less stuttery now?
It's less stuttery.
How's that?
Why don't? That's better. Why don't we can try your image now? Why don't we? I like to see people giving talk, so I think we can risk seeing you.
Okay, how's that then?
That seems good. Let's try it.
Okay.
Sorry.
Okie dokie. It might be me that's stuttering actually. Okay. So going through the axioms again. I mean, at the end.
I'm sorry, Gordon.
So this derivative d of f.
Gordon, I'm sorry. We've decided that the video is
Okay.
the problem.
Hello.
So you have to turn off your video and hope that helps. Sorry. We should have done this all
help in
before.
some respects. Let's see. How's that, folks? Is that better? Well, I'll keep talking. Fab to everyone. Seems better. Anyway, it can't get any better than this fab. So, so d of f is actually linear in the second argument, not just additive, by which I mean its derivative doesn't depend on where you're taking the derivative. So you have to have this extra argument, extra axiom saying that. And finally, symmetry, which is saying that if a differential with respect to x, then y, that's the same as differential with respect to y, then x. So that's a natural bunch of axioms. And probably if they'd missed out one, it would have come up in their categorical investigations. But why should that be the right bunch of axioms? If you want to have characterized as smooth maps, certainly these are all true of the smooth maps, but how do you know you haven't missed out some truth about the smooth maps? So that's a natural logical question. It's a kind of completeness question or a coherence question. And that's the kind of thing I got interested in. But I thought, first of all, rather than working with differentials of functions from m to n, let's just work with partial differentiation. That's a kind of a simpler thing to think of. That's where people start off with. And how about some axioms for partial differentiation? So here are some axioms for partial differentiation. Plus and times. So, and I want to say that we have a commutative ring. So we get the polynomials. I'm adding in the reals and the multiplication tables for them because I really think about the smooth functions and working with them. But you could miss them out, and the more basic theory would not have them in. And you'd think what happened if you added different kinds of constants. But let's leave them in just now. So what axioms are there? Well, we know what the partial derivative of addition is. There it is. We know what the partial derivative of multiplication is. There it is. We know the chain rule. But the cute thing is I'm just going to put in the binary chain rule. I had the general chain rule in originally, but Sam Staten made a very helpful suggestion. And the axiomatization has now come out finitary like this. And finally, commutativity, that's dy by dx, the same as dx by dy. So in reading that, you should see two kinds of variables, ordinary variables like x and y, and function variables like f and g. And we can substitute syntactic versions of functions for the function variables. I'll show how that works later, and terms for or expressions for the ordinary variables. That's the idea. So for example, we could substitute nothing for x in the axiom for addition, you'll get dx by dx is 1. Or we could substitute nothing for y, sorry, I should have said y. And we should substitute nothing for y in the axiom for multiplication, and you'll get 0 by dx is 0. So there's some little theorems. But the question is, what am I talking about? In what sense is this a formal axiomatization? In what sense can we draw conclusions? Well, we want to do equational logic. So let's just quickly rehearse standard equational logic, which goes as follows. You have some operations of some degree or rarity, op colon n. You can make terms from variables and operations. And rather than writing things like plus of e and e prime, we might prefer some notation like infix notation. Axioms are a set of equations. And then the logic works by you assume the equations, you have the usual, some obvious rules for characterizing equality or equivalence relations. You have a congruence rule, saying you can substitute equals for equals in functions when applying functions. And finally, the variables in there are supposed to be universally quantified logically, so you can substitute any expression for any variable in an equation. And the theorems are whatever you can prove that way. So that's the standard equational logic. And almost obviously, the axioms for partial differentiation don't fit in that way because we have binding variables, binding structures. So let's look at some notation for partial differentiation. So people sometimes write things like df by dx for some function f of x, y, but that's kind of terrible because what you're differentiating with respect to is somewhere else in the text way over. So it's better to write d of f of xy by dx. That's an improvement. And that's a function at x, a function of x itself. So that's not so good. We should really say what we're applying the function to. So a natural notation is dE by dx at some other e. Or you can write that partly in the Leibniz way, dE by dx, where x is E1. But that's actually kind of bad too, because the x is acting both bound and, no, actually that's okay. But x is occurring in a bound way twice. It's not so nice. The original one's a bit better. Then some other abbreviations are just the usual dE by dx, and then that's a function of x. But now it's just an abbreviation for dE by dx of x. So it now makes sense. I just want to be able to use these things. But just as infix is nice, you need a boring notation. So we need a boring notation for partial differentiation. So that's going to be p diff of two things. The first thing's a syntax for the function you're differentiating, x dot e naught. This function was given x gives e naught. And the second thing is what you're applying the resulting function after you've done the partial differentiation to, namely e1. And that can be written nicely as on the right or properly as on the left. So what are the expressions? We're basically trying to get towards a version of equational logic, but not the standard one. So we have reals, variables, plus and times, applying function variables f to some arguments, and partial derivative of a function at some argument. So there's a few things one has to get under one's belt, which are a bit weird, perhaps, which is substitution. You remember that in ordinary equational logic, we used to do substitution, so we need to do substitution here, and that's done, I guess it's the way you'd expect, but so when we substitute an expression in an application, we just substitute it in the arguments of the application. When we substitute it in a partial differentiation, we substitute it to e naught and e1. But as always with bound variables, we have to choose y and x so that there's no clash. We're also identifying things up to alpha equivalence, if that means something to you, which I hope it does. And I've written the second equation twice, once using the boring notation, once using the ordinary notation. Okay, so now comes something a bit nastier, which is how do we substitute for function variables? So the idea is that we substitute for a function variable an abstract. So it's this x naught dot through xn minus 1 dot e. So that's, as it were, the function that we're going to substitute for f. It's the function which 2x naught through xn gives you e. And probably the best thing to do here is to read the second line first. So if we're substituting g of e naught through en minus 1, where g is a different function variable from f, we just do the substitution in the body, right? What happens when we substitute it into f itself applied to some e's? Well, we still have to do the substitution for all the e's, e naught through en minus 1, but now we know what f is, so we better substitute, when we get the results of substituting into the e naught, etc., we better substitute them for x naught through x minus 1 into e. So that's a nasty definition to try to get your head around. With partial differentiation, you just substitute in and you're careful to avoid clashes. But I think there aren't any clashes because you can't clash an ordinary variable with a function variable. So I'm assuming from no questions that you're okay with that nasty thing. So that's good. Okay, so carrying on, equational logic is the axioms for, we've said what the axioms are, and the above axioms I started off with are now written, you could read them as written in this formal notation. And we have analogues of, we have the previous kind of, so we have the natural congruence rule for the partial differentiation. You can substitute equals for equals inside the partial differentiation. And as the ordinary substitution, we allow ourselves also to substitute abstracts for function symbols. Somebody says, I think it's conservative, okay, over something. Okay, so and we get theorems. So here's some examples of some theorems. So it's just a little exercise. Suppose I want to prove, for example, that dy by dx is 0, where y isn't x. What I can do is I can use the binary chain rule, which I've got there, and I can basically blank out everything. So I can make f the function which gives you y constantly, ignores its argument. So I'm going to substitute x naught x1 dot y, that's abstract for f. And I'm going to use g naught and g1 to blank out. So they're going to be the constantly zero function. So when I substitute all that into there, I get dy by dx is something times d0 by dx, because g of naught of x is going to be 0, and similarly over there. But we know already that d0 by dx is 0, so all the and this is a multiplication, so we get 0 at the end. So that's the easy one. The unary one is similar, except you don't blank out to the left, and you do blank out to the right, and you get the unary one. Leave that as an exercise. And then with a good deal more work, you can, so we've got the binary chain rule, so we get the cases 0 and 1, but also we get all the cases greater than 2, and that's the standard version of the chain rule, and that you do by a not very pleasant induction, by an induction. An interesting thing is, as well as writing it out in the standard way, there's a nice substitution version, and that's interesting because it tells you how substitution and partial differentiation interact. If I want to take the partial derivative with respect to x of something I get by substituting, first of all, I take the partial derivative of it and then substitute, and then multiply by all the partial derivatives of what was being substituted in, and I add it up. So that's kind of a cuter, a more pretty kind of way of writing the chain rule, but the two are equivalent, as one can easily show. Okay, so what I want to point out now is that, so this isn't an ad hoc thing. There is a general notion of equational logic with binders, which is due to Marcello and his students.
I think you expanded your slides a little bit.
Well, notational variation.
I think you expanded your slides a little bit, which is now they're fading off at the edge for some mysterious reason. Yeah, sorry.
How's that? Sorry, so I could read it better, but so you could read it worse. Anyway, I'll put it back again. Maybe I'll put my glasses on. No, I won't. So here's some example binding operators, which you'll have seen, but just to show they fit in. Integration is a binding operator. It binds the E and a couple of arguments A and B. And it'd be interesting if anyone felt like writing down the axioms for integration. I'd quite like to see them. But that is being done categorically, so there's corresponding questions there. The ordinary untyped lambda calculus is another example. I've written just below example equations, which are just the usual beta and eta, and they're natural to write in that way. You could do algebraic, this is algebraic logic as it should have been done, with binding operations for all, and it's good fun writing down the predicate calculus equationally. And then one point there is that I'm using multi-sorted version of things because I'll have a type of objects and a type of truth values there. And then one thing, I was wanting to get an example. All three of those binding operators take exactly one abstract and 0 or more ordinary arguments. I'd like to find an example in mathematics which takes several abstracts, but I couldn't find any. I don't know any. I'd really like to know one, if anyone knows one. But if you go to linguistics, there's these things that are called generalized quantifiers. There's lots of examples. And here's one: most P's are Q's. And what logic for that, I have no ideas, but it takes two abstracts. Okay, in general, the type of an operation is it takes K abstracts, where say the first abstract is M naught long, and so forth. It takes M naught variables and N ordinary arguments. So that's the type there. And then it's worth having just some syntax for abstraction in general. So we write A as X naught through XM dot E, and then an expression is gotten by applying an operation to K minus 1 abstracts, each of the right length, arity or whatever, yeah, arity, and N ordinary arguments. So that's their equational logic. Let me jump back now to semantics of our partial differentiation theory, then I'll maybe say a little bit about semantics of such logics in general. But here it's very easy. Oh, something's gotten missing. That's strange. Oh, well, I'll just have to say what it is. I think it's defined a few slides later. So the semantics of an expression E is defined relative to a phi and a rho. What rho does, it's the ordinary environment, and it assigns reals to every ordinary variable. and rho is a function environment and it assigns smooth functions to function symbols of arity n. I should have said earlier that every function symbol comes with a built-in arity. And the only somewhat interesting definition is the last one, which says that if I want to see what some partial derivative type expression denotes, I look at basically the semantic function x dot t is denoting, and I take its derivative. It's not obvious from this definition that it's a proper definition, because how do you know that that thing you've defined is smooth? So to show us a proper definition, you have to inductively have some hypothesis that you pull through that says it's smooth, but that's straightforward. Excuse me. Oh no, it says what the environments do here just a bit later. So validity is just defined to mean E naught equals E1 is valid if they have the same meaning, i.e. they have the same denotation for all environments. This is a concrete semantics. This is semantics made out of real functions. But in general, you don't get a good theory, and you miss lots of examples if you insist on being concrete. This is one notion of the general kind of thing. You can look in Marcello and everyone's papers to see the general notions or equivalent versions. But what you do is you take an abstract clone, C, which is the same thing as a one-object Cartesian multi-category. And for each operation, you might think that the operation goes from C of M1 cross C of MK cross C of 0 to the power N to C of 0, but it doesn't. You have to allow parameters. So it has to be a family of such things. So it goes from C of, if you've got P many parameters, it goes from C of P plus M1 times a lot of things, cross C of P to the N to C of P. An example of such an abstract clone could, for example, be all polynomials over some ring. That's certainly an example that'll work fine, including multinomials. I'm not a polynomial several arguments meant to say. So the semantics is for each expression in context E, it denotes a function from the values in the clone of the function variables to a C of M, because it's basically a thing going from x1 through xn to E, and those such things are in Cn semantically. So that's the general idea, but I just want to give a hint. If you want to know more, read those papers. I want to spend most of the time on this actual particular theory. So everyone knows what consistency and completeness is. Consistency is if you can prove it is true, valid, and completeness is the converse. But we can also talk about polynomial function environments where all of f's are polynomials. So we could have polynomial completeness, which is that if the E naught and E1 are equal, not necessarily for all smooth functions, but only for all polynomial functions. And that's polynomial equality, and this would be polynomial completeness. And that's what we're going to prove, because polynomials do lots of things that are nice. So here's the proof strategy. So you might think the obvious thing to do to prove completeness, well, is to, so if two things aren't equal, can't be proved equal, then there's some polynomial functions that'll separate them. And that is indeed what you want to prove, but you don't do it that directly. You'd like to do it through normal forms, but normal forms are a bit not so clear or nice, perhaps, in this setting. And so I do it with things that are as good as normal forms for my purposes, which I'm going to call canonical forms. And so for every expression, we're going to define its canonical form. And what we're going to do is it's going to be an effective definition, because we like our logic to be decidable also. And we're going to define an equivalence relation between canonical forms such that if two canonical forms are equivalent, then they're provably equal. And what we want to show, oh my goodness, is that 27 minutes already? Is that if two canonical forms are different, then we can separate them by some polynomial function. And this gives you the contrapositive of completeness if you push it through, because if two things aren't provably equal, their canonical forms can't be provably equal, so their canonical forms can't be equivalent. So that means we can separate them. So that means we can separate by some polynomial, so they can't be polynomial equivalent. But since E and CF of E are provably equal, they're also equal in all environments because we've got consistency. So that says that they can't be provably equal, and that is the contrapositive of completeness. So we'd prove completeness if we proved all these other things. Now that implication we can take around the whole, we can turn it into positive and we can make a loop. And so with consistency completeness, we get that you can prove E equals E prime if and only if their canonical forms are equivalent. So constructing canonical form will be effective, and being equivalent will be effective, so equality will be decidable. Okay, but how on earth are we going to do this? So I want to say a little bit about this, and it turns out to be interpolation, which is very nice. So suppose I've got just two functional expressions, g of f squared of g, and I want to show that's different from g of f of g. And I want to do it by taking g and f to be polynomials. How do we do that? Well, there's a bunch of sub-expressions, g of x, f of g of x, x. Just let's give all the sub-expressions numbers 1, 2, 3, 4, 5 like that on the left, and 1, 2, 3, what's that, 6 on the right, because some sub-expressions occur on both sides, so you have to give them the same number, because we want these numbers to be the value of the polynomial functions. So for example, if we set x to be 1 and g of x to be 2, we have to choose g so that g of 1 is equal to 2. So, my goodness, can you still hear me? Okay, it sounds really weird at my end.
I think we hear you fine.
Okay, it's like the C at my end. Okay, so if you write all these requirements down, you get, for example, that what have we got? G of 1 is 2, G of 4 is 5, and G of 3 is 6. And then we can find such a polynomial by doing Legendre interpolation, and that's a standard formula. And I'll just pretend that you've had enough time to read it, unless you want me to go tell you. So how about, so that's as it were step one. We're still a long way from expressions in the theory of partial differentiation, but let's go on to say binary functions. So here's, suppose we want to show that f of gx, gy isn't always g of f of xy. So I'm using trees now. So for example, we'll label all the nodes of the tree by different numbers, but as long as but equal trees, we have to label by the same number. So there's a bunch of labelings by numbers. And if you look at, say, f, it occurs twice. So obviously we want f of 3 and 4 to be 5, and f of 1 and 2 to be 6. But there's a multivariate version of Legendre interpolation, and I've written a formula there. It's logically the same as the previous formula, but instead of saying that the distance from x and 4 is x minus 4 without worrying about sign, you take the Euclidean difference between x and 1 and 1, 2. And since that's the square root, you don't want that, so you square it. So you get back to polynomials. And it's the same logic as before. I'm not trying to be efficient, it's just being simple. So that's great. But then there's partial derivatives, so they're going to come in too. So just remarking to the top that if you've got a binary smooth f and it's binary, and we take a k partial derivatives of it with respect to x1 through xk, these i's can be either 0 or 1 because you're either differentiating with respect to the first argument to the second argument. Then these m's, these sequences of where you're differentiating, give you differential operators d sub m applied to f. It just enables you to write these things rather more neatly than writing out all these partial derivatives. Okay, so there's a couple of sub-expressions, and you'll see basically by exactly the same reasons before, we get interpolation conditions, but now these interpolation conditions involve partial derivatives. We want that of, what is it, dy by dx naught, no, dx naught by dx1 of f at 3 and 4 is equal to 5 and so forth. And it's far from obvious that we can solve such interpolation problems. And the first person to work on this was Hermite or Hermite, someone can correct me, who solved it in the unary case, and Severi apparently solved it in the general case in 1930. So there's just a definition of it. A multivariate Hermite interpolation problem of dimension d is given by a finite set of nodes. Those are the places, the arguments to your functions that you're given in. And for each node, a bunch of partial differentiation conditions. They all have to fit together. And Severi says every such problem has a solution by a polynomial of a certain degree, which is really beautiful theorem. And that reference is a place that you can find an explicit proof of it. Okay. So, however, this is still not there because our expressions also, unfortunately, have polynomials in the middle, and we need to control them as well. Are we doing? Yeah, doing okay. So, forgetting about the differentials for a moment, let's just go back to expressions we had before: functions, unary and binary functions. And let's assume some polynomials as well, P and Q and R there. As a kind of, so we're thinking of kind of layered expressions. We have a polynomial, then some functions, then some polynomial, then some functions, all the way down to the bottom. At the very bottom where the x's and y's are coming in, you can think of the trivial polynomials, which are just variables. They're kind of there implicitly. And there's a kind of a duality. The output of the polynomials is the input of the functions, or else it's the output of the whole expression. And the input of the polynomials is the output of the functions, or else it's the input of the whole expression. So it's a kind of slightly odd thing. Okay. So how are we going to deal with this? We don't have complete freedom like we had before. If I tell you the inputs of the polynomials, you'll tell me what their outputs were. So what we have, but we do have a bit of freedom. If we have a bunch of polynomials, then it's not hard to find values for all their inputs which differentiate any two different polynomials. So that's what we're going to do. So suppose we've chosen all these values, then we know the inputs of all the f's and all their outputs. And that's that's an interpolation problem. We'll solve it, and that'll do the whole thing. And what we'll make sure of is that because we've arranged different inputs for different polynomials, that the whole terms will be different. But there's a slight thing there that's not that clear. What are the actual polynomials, right? If you look at, say, P of fg, that's going to be some polynomial P of xy into which you substituted f and g. But there's another occurrence of P in the right hand. That's the same Pxy, but you substituted different things into it. So we want to be able to substitute different values for it. So the first polynomial row is P of xy. You should really think of it as P of some, say, v0, v1. And the second polynomial, since the things there are different, it should be, say, v2 and v3. We have to adjust the variables to get things correctly. And that's a bit of a bother. And I'm not sure I'm going to go into it. I think what I'll do is, if anyone wants to know more detail how we do it, I can show you through a worked example. No, maybe I'll say a little bit. Let's try a little bit. So if we look at this, yeah, if we look at this example here, actually, I do want to say something. We can enumerate all the atoms. And by an atom, I mean a subterm which begins with an operation like f of q of g of x, q of g of x. So these atoms, to get the right polynomials, we're going to have to replace them by variables. We're going to call them interpolation variables. So these are v1, v2, v3. What I won't go through the details here. Now, once we know these variables, we can see what the polynomials that we have to separate are. So P of xy, the interpolation variable for f is v1, interpolation variable for g of stuff is v3. So the polynomial there, which I'm going to call the node polynomial, better call it interpolation polynomial, is P of v1, v3. And we get the other P is v4 of v5 with a systematic way of proceeding. So we choose values A's for the V's, which give different outputs B's for the different polynomials. That determines our interpolations. There's the ones for F, and we go ahead and solve. So that's how things work. And so what I want to do now, 640, 50, I guess just very briefly is try to give some idea of how the actual proof works. So we have to somehow get a syntactic analog of these d sub m's. So we have some f sub n, which is gotten, this is now in the formal theory by doing some partial differentiations, some substitution, but just think of it as the same as before, but just formalized. Now we have to say what the atomic expressions are, the f's of things. We have to say what the canonical forms are, that's the polynomials of things. So a variable is an atomic expression, an f sub m of some canonical forms, which are basically going to be polynomials of atomic expressions, are atomic expressions. And if you've got a polynomial with all the x's occurring in the polynomial, and you substitute some atomic expressions, then you get a canonical expression. So these are the layered kind of things we had before. And then canonicalization lemma says that you can canonicalize any expression by doing lots of partial differentiations. You just use the usual formulas, chain rule, and how plus and time works until you hit a function symbol, and then you accumulate on the index of the function symbol. It's straightforward, moderately straightforward. So I need to define now equivalence of canonical expressions, and that's defined. First of all, I have to define equivalence of atomic expressions. So two atomic expressions are equivalent if the operation symbols are the same and the sequence of partial derivatives, the m's, are the same. They don't need to be exactly the same. Because of commutativity, we can permute. So they have to be the same up to permutation. And the canonical expressions have to be equivalent also. So that's an inductive definition. And the definition for the canonical expressions is more complicated. I don't want to say how that's working in any detail, but what it is, it's a general thing which is constructing interpolation variables in the way that we pointed out in the example. So once you've got the interpolation variables, you know what the polynomials are because you look at where's it gone to? You look at the p of x naught through x n minus 1, and you substitute the interpolation variables that you've calculated for it. And so then two canonical expressions are the same. And you say that's the canonical. Once you've done that, you say that's the canonical polynomial of the canonical form, and then you say finally that two canonical expressions are the same if it's the same canonical polynomial. Now it's reasonably obvious that this is decidable, and the proof is inductive. So here we carry the induction through by size, and to do this, we need to see which atomic sub-expressions are equivalent. But we can do that by induction. And once we know that, we can then characterize the interpolation polynomial, and then we can see whether two polynomials are equivalent. So this just means they're equivalent up to the ring axiom. They're equivalent to the usual sense of polynomials. Okay, so that's good. And then we, of course, have to prove our theorem. And what we prove is a separation theorem, that given any finite set of canonical forms, there's some polynomial function environment that separates any two ones that are inequivalent. And that's done basically, you saturate your finite set of canonical forms by closing them under sub-expressions, and then you get all the interpolation problems, you solve them all. For every function symbol, you solve a Severi type interpolation, and you use that to build up, that determines your function environment, and then you use that to build up to show that you have what you want by some inductive arguments. It's a bit complicated, but it works fine. And as I said, it's decidable. So these are the main theorems. So this is the kind of thing that you want to prove. And in some sense, the talk could end there, but I've got some more to say and some more time to say it. So this is semantic completeness. It means that in some sense, your axiom system is very good because all the axioms are true in the model you care about, and only those are true because you can prove you can have all truths. But it doesn't follow that you couldn't add some extra equations. There could be some mysterious extra equations which aren't true for smooth functions, but hold in some other model. And it'd be nice to know that that's not the case. So we say an equational theory is inconsistent if it proves x equals y, and it's equationally complete or Hilbert post-complete if it's got no consistent extension. So a simple example of that is the theory of semilattices, that's commutative monoids and x plus x equals x. And that is equationally complete. Consider any equation. We can think, we've only got variables and plus and zero. So we can think of any expression as a sum of variables. And we can delete repeated variables. So any equation is a sum of unrepeated variables equals some other sum of variables. So suppose there's a variable, if there's the same variables on both sides, that's a reflexivity anyway, modular reordering. If there's a variable on one side that's not on the other, say x, then you can set all the other variables to 0 and you get x equals 0. But if x equals 0, then y equals 0, so x equals y. So that shows if you add any unprovable equation, you get inconsistency. So that's nice. And what's nice is that that's also true for us here. Okay, so this is the proof of equational completeness. I'll just try to give the idea, I guess. So first thing is by completeness, that if I take a closed expression, that's an expression with no free function variables or ordinary variables, then that just denotes some real. So let E, for example, denote R. So if E denotes R, then it's valid that E is equal to R, but then by completeness it's provable. So we can prove every closed expression equal to its own denotation. So that's a handy thing we're going to use. Now, let's take our theory and add some unprovable equation E naught equals E1. And just to make the argument simple, just suppose E naught and E1 have no free variables and only one free function variable, which is unary. So by polynomial completeness, since it's unprovable, I can find a polynomial environment which differentiates them. But that polynomial is definable in our language because I've given you all the real constants. And it turns out that the meaning of an expression in which you alter a function environment by substituting the meaning of some polynomial is the same as the meaning of the expression with the polynomial substituted in. So in other words, substitution and denotation commute. That's a kind of a standard thing, true in all equational logics and true in this one too. So that means that you have these expressions, E naught, I'll call it E naught prime, E naught with this PX substituted in, and E naught and prime and E1 prime, at least it would be if there wasn't a bug over there, are closed expressions and they denote different things. So let them denote R and S. These are different real constants, and we can actually prove them equal to what they denote by the previous remarks. That means there's two real constants, assuming the axiom R and S, that we can prove equal, but they're different reals. So that means that if I can prove R equals S, I can prove R minus S equals 0. Dividing by R minus S, since R isn't equal to S, I prove 1 equals 0. Multiplying by X, X equals 0, so I get X equals Y, so it's inconsistent. So that's nice. It's not only are the axioms those that are exactly those that are valid in the smooth functions, you couldn't add any more. How about other cases? Suppose instead of real constants, we allow, say, rationals. Well, we'll still have completeness, because if we can separate out using reals, since everything's continuous, we just move over a little and separate out by rationals. And this argument will go through too, the completeness where R and S are different rationals just as well. But suppose we just don't even have any rationals, we just have 0 and 1, which is the same as having the integers since we've got ring theory. And it turns out you still get completeness, okay? Wait a minute, yes, that's right, because you haven't done anything very much. But only relative to, yes, that's right, I think if I remember correctly, you get completeness relative to, just to the polynomials you can define using the integers, that's right. But you don't get equational completeness because we can set 1 plus 1 equal to 0. And there's a very cute counter example, which is, I found out you can differentiate Boolean functions. So suppose that f is a Boolean function and we want to differentiate it at x, I, you just look at the value of f at 0, the value of f at 1 and add them up. So plus is a Boolean plus exclusive or, and times is Boolean times, which is and. That's a really mysterious definition. And it got less mysterious to realize it could be rewritten as, if you just ignore the other arguments, let's say df by dx is f at x plus dx minus f at x divided by dx. As long as you set dx to be 1, it's the only possible differential with the Booleans. And so these two functions, these two definitions are the same, so it makes more sense with the second definition.
Has anyone used differentiation of Booleans?
Another thing you can use is Booleans formal differentiation. Yes, right there.
No, it seems like it could be something really useful. I never heard of it, but it seems like it could be really
it was invented
useful.
by engineers to be useful.
The differentiation?
A bunch of engineers, and if you look up in Wikipedia, whoever wrote it, yes, yes, it's
great.
Well,
okay.
It's been around for ages. And the,
cool.
and the Wikipedia article claims it's very useful. It's used for coding theory and all kinds of things. I haven't read the uses, but anyways, it's a kind of a cute thing.
Yeah.
So now you know you can differentiate Boolean functions. Yeah. Okay. So let's go back to where we started, Cartesian differential categories. So the authors, Seeley and Crockett, they actually did have a type theory. So the type theory is not quite theory of the kind we had. It's slightly different, but it's essentially equivalent to one, which is. So what we'd use is we introduce a different kind of operation, this D. Remember the differentiation there, differentiation a function at an argument, then you apply it to some vector. So intuitively, so you need two things to apply it to. So that's the E1 and the E2. And so now they have this, Crockett, Blues and Seeley have this partial differentiation notation, d naught by dx at E1 and then dot producted with E2 intuitively. So it's sort of the same as before, except for this dot E2. And then you can get variance, the usual notation. And the axioms now become nicer. And I think these axioms will be equivalent to their axioms. And the question is, can we apply the same, versions of this technology to show this is also complete? And I think we can, but I can't tell you yet. So I'll stop talking and say thank you.
Thanks. Great.
Okay.
People have questions.
Oh, I can put it.
People are clapping.
I'll dare to put. No, I want to wait.
I mean, I have kind of a silly question from earlier. I mean, I actually kind of know this binding algebra stuff, but I've also noticed in practice you can usually just work in kind of first order logic, and then you add higher order types, but no comprehension schemas, and then you just add lambdas, and then it turns out that you can that just with lambdas you can define just a bunch of equations, and you don't need any other binders usually. Just lambda is enough, and then beta, and this is kind of the automath trick, right? I mean, it's just lambdas, and then that's your only binding construct. So I was wondering if, I guess this is a little bit out of the scope of the paper, but is there a reason to not just use lambdas and work modulo beta?
Is there any reason to use lambdas? Why not just use natural notation?
Well, sure, but it feels like here you introduce arbitrary.
I mean, well, from a categorical point of view, having lambdas means you're in something like Cartesian closed categories, and here we're not assuming all of that. This is what you have if you're just in almost a first order situation.
Yeah,
and you can define lambdas in it anyway.
Right. If you just have simple types, then your theory is conservative. It's not trivial, but it's true.
I don't have simple types. But I don't have simple types. I've just one type. It's just equational logic. It's a very, very simple thing. It's not any kind of predicate calculus.
Okay.
Matter of taste, I guess. I mean, you can see if you want to see the lambdas where I wrote binders, stick lambda. But then you'll be using real second order functions, and I'm not. I don't want to use real second order stuff. I want to axiomatise it without assuming comprehension or anything like that.
Sure.
But that's why you have to allow non-concrete models to make it work. Yeah.
All right. And my other question is, if you add kind of Boolean combinations, are you still decidable? That seems less obvious.
Oh dear. Just Boolean combinations.
Yeah,
I'd
and
keep
then
the
my next
universal
question
quantifiers
is
inside the Booleans
now add
or outside.
quantifier alternations. Right, because the theory of
I mean the theory of rings is undecidable, so it won't take long before you get undecidable.
Yeah, but polynomials over
Hello?
reals is decidable.
The theory of the reals is decidable, yes. But what about partial differentiation? I don't know. I mean, there's lots of good questions. I don't know all of them. I mean, something that's very close to this is a differential rings. There's been huge amounts of work done differential rings and differential fields. And you could look at that. I mean, there's infinitely many questions of that sort. I'm just doing simple ones.
You're just doing finitely many?
Can I ask something?
Many questions here, right?
I'm really impressed that this
look at that.
That this is decidable. It's really incredible. So I guess the next step is to sell this to Stephen Wolfram and implement it in Wolfram Alpha. No, I mean it really should be in these. I mean, this equational theory should be implemented.
Yeah, it seems like a very basic equational theory. I mean, it's been around for 300 years. So.
Indeed. I mean, it's incredible.
Explicit. Yeah. Well, actually, I looked up the partial differentiation. It was actually 1800 and something that it was into the way of something. 1880 something.
So I think. Oh, go ahead.
Yeah. This is I hate to bring this up because I know almost nothing about it, but Jerry Sussman was working on these classical physics books a while ago, and one of the big points that he made was that the proper notation is incredibly ambiguous, and I wonder if what you're doing has anything to do with his project in mechanics.
I don't know. That's an interesting question.
There's a scheme.
You're really breaking up pretty badly, at least for me, Gordon. I don't know if that's just me.
Okay.
I'm thinking maybe we should repair to the online chat room where we can converse by typing at a low baud rate.